And Pedro and Humberto work in a field called symplectic dynamics that is relatively new. And it basically consists of applying rather sophisticated techniques and methods from symplectic geometry and topology to understand dynamics of Hamiltonian systems. So we'll see more about that in a little bit. And the field is very broad, and I think it's very welcoming to young researchers and students. I want to say a few words about them. Humberto was a student at the Federal University of Rio de Janeiro, where he got his undergraduate degree and master's degree. And then he moved to New York, to NYU, where he got his PhD under Helmut Hofer, in 2008. Pedro studied at University of São Paulo, and he got his PhD there under Clodoaldo Ragazzo. And he later went to New York as well for a postdoc period, also under Hofer, and that's where they met. And after meeting in New York, they started this really fruitful mathematical collaboration that culminated, I think, with this really beautiful and prize-winning piece of work that we'll hear more about now. So let's welcome them.
Thank you very much for the introduction. It's an honor for me to give this plenary with Humberto on our work. As I mentioned before, there is a third author, Nome, and so we have a version of the poincaré-Birkhoff fixed point theorem, which is originally for two-dimensional maps, and we have it for three-dimensional flows. And the reason why we have this type of result is that we consider Reeb flows. It's a class of Hamiltonian systems with a lot of structure, so that we can use very powerful analytical tools to prove results such as existence of periodic motions. Since these flows can be seen inside a complex manifold, and we can talk about holomorphic curves, and periodic orbits, the existence of them are somehow equivalent to the existence of some holomorphic curves. And it's remarkable that in the end, it's easier to work with such holomorphic curves instead of working directly with periodic orbits. So I will remind a little bit of the original, how this poincaré-Birkhoff theorem started. So Poincaré studied the three-body problem with a lot of symmetries. And so, for instance, you study the motion of the third body, which you assume that has no mass, while the first two bodies are moving in circular trajectories. And there you see the Hamiltonian function describing the motion of this third body with no mass, which depends on a parameter. Here you see mu, which is just a parameter related to the masses of the first two bodies. So the Hamilton's equations, if you integrate them, then you have the trajectories describing the motion of the third body. And even if the Hamiltonian function is quite simple, to prove an existence result of a periodic motion is extremely hard. But Poincaré succeeded to do that, to prove these periodic orbits. How? For certain values of the energy and certain values of the parameter, he showed the existence of global surface of sections, of annulus type. So he found very special annulus inside the energy level, such that the dynamics inside that energy level could be reduced to the first return map. All the trajectories would hit that annulus, and instead of studying the three-dimensional flow, you could now study the first return map on that annulus, and this return map had a lot of nice properties that I will just put it now and state the Poincaré-Birkhoff theorem, which was the following. This map, this homeomorphism of the annulus, it preserves area. It's homotopic to the identity map and preserves area. And it satisfies a topological condition, which is it twists the boundary in opposite directions. So the notion of twisting the boundary components in different directions is the following. If you take a lift of this map to the strip, here are copies of the annulus, then the map restricted to the boundary components move the points in opposite directions. That's what I mean by a twist condition. So when you have a map with such properties, so homotopy to the identity map, preserving an area form, and twisting the boundary components in opposite directions, then this map has two fixed points. Okay, so that's the classical version of the poincaré-Birkhoff theorem. I will just, which is important for us, to put a very special case where we have a very simple proof of this theorem. It's very hard to prove the general case, but if you assume some nice properties of the map, then you can give a simple proof using Morse theory. So let's suppose that the map can be written in that form that I showed there, okay? So this map is, in fact, the identity map plus one term here that you see is just the gradient of a function, which I call a generating function, defined on the annulus, rotated by 90 degrees. For instance, if the map is a diffeomorphism C1 close to the identity map, then such generating function exists. Okay, so let's give a proof of this theorem, assuming that the map is in that form. It's not so difficult to see from this form of the map here that the following holds. This generating function, which is a real function on the annulus, it is constant along each boundary component, and because of the twist condition, the gradient of that function points outward. And so the minimum point of that function is an interior point in the annulus. And if you see here this form of the map, a critical point must be a fixed point of the map. So since with the twist condition we can show that the minimal value of the minimal point of S is in the interior of the annulus, then we have found one of the fixed points. And the trick now is just if there is no other point of minimum of this generating function, then you can apply a very simple minimax procedure to find another critical point, which behaves like a saddle. And that's our second fixed point, because another critical point of this function is, again, a fixed point of the map. So here is a very simple way to prove this theorem under this extra assumption. Of course, the general case is very hard. For instance, if you are close to the identity in some good topology, then you have this type of proof. But if you are far away from the identity, then things start to become much more difficult. And that's in fact, Poincaré was trying to prove the existence of infinitely many periodic orbits for the restricted planar circular three-body problem. And with that theorem, as you see, if you have reduced the dynamics to a annulus map, you have those fixed points, those two fixed points, which are periodic orbits for the motion. But if you iterate, it's possible to see very easily. If you consider very high iterates of the map, these high iterates are also twist maps. They also satisfy that twist condition. In fact, as I said here, the twist condition, you consider a lift to the strip, and you see points in one boundary component moving to the right, and the other boundary component moving to the left. So you have a rotation number of this boundary component, and this rotation number is positive, and this one is negative. So that's what I put here, rho plus and rho minus. And if you take any rational number inside this interval, determined by rho minus, rho plus, any rational number, you can associate at least two periodic orbits. So if it's P over Q with no common factors, you can find a periodic orbit with period P, with period Q. And this P means that this periodic point somehow rotates around the annulus with velocity P over Q. So for each P over Q inside this interval, you have these periodic orbits which are somehow rotating with this rational velocity. So you have infinitely many periodic orbits for this map, and so you have infinitely many periodic orbits for the restricted three-body problem. So this is the Poincaré approach to prove existence of infinitely many periodic orbits. So a little bit of the story of this theorem is that Poincaré, in fact, was a conjecture. He didn't prove the whole theorem. He just proved in some case, which was enough for the three-body problem. But in the beginning of the paper, he says, well, I'm sorry, I will not give the whole proof, but I don't know if I will have another opportunity to write again about this problem. And in fact, a few months later, he dies, the same year that Birkhoff gives a proof of the general case. But Birkhoff was, I believe that the proof of the second fixed point was not completely clear, or maybe there was a mistake. And Birkhoff again published another paper with some other subjects, but trying to fix the proof of the second fixed point, but still the second fixed point was kind of polemic. And later, only in 1977, Brown and Newman took the ideas of Birkhoff and said, well, this works. And they wrote a paper very carefully on those ideas and showed that, well, it's correct. The second fixed point is there, nothing wrong. It's just maybe not well written, but everything was okay. And this paper in 1990, Golay and Howe, they proved the Poincaré-Birkhoff theorem following exactly the ideas that Poincaré left in that original paper. And I put here another, of course there is a vast literature about this theorem. It's just a few comments about this paper by Crecjarto, that he, at the same time of Poincaré, Brouwer was developing his theory of homeomorphisms of the plane without fixed points, homeomorphisms which preserve orientation. And Crecjarto unified these two theorems, proving, giving a single proof for both of them, for Poincaré-Birkhoff theorem and this Brouwer translation theorem. And you can see here that this essentially Poincaré-Birkhoff theorem might be a topological theorem. There is this hypothesis of preserving area, it's geometric, but you could replace it with a topological hypothesis and have a theorem just in the topological side. But anyway, I won't go in that direction. I'll go in the conservative direction, which you see this hypothesis of area preserving. Okay? So in the 60s, Arnold realized that there is a way to generalize Poincaré-Birkhoff theorem for conservative dynamics, for Hamiltonian dynamics. So I will state Arnold conjecture, which is the following. Consider a simplex manifold, which is an even dimensional manifold equipped with a closed two-form, which is non-degenerate. Assume that M is closed, connect, just to simplify. And take a function on the manifold. It might depend on time, so it's a function here on R cross M. R, you have this time parameter. And then with this function, it's the Hamiltonian function on M, let's assume that it's periodic on T. One periodic on T, okay? So the Arnold conjecture is related to the existence of one periodic orbit of the Hamiltonian flow. So with this function H, we have the Hamiltonian vector field, which is just a vector field that you contract with the symplectic form. You have this one form given by the derivative with respect to M of the Hamiltonian function. And you consider the Hamilton's equation, x dot is equal to Hamiltonian vector field at x. So you consider this, the isotopy generated by this vector field. And this conjecture is about existence of periodic orbits with period equal to 1. The Hamiltonian functions is one periodic, and we look for orbits which are also one periodic. So there is a trick, I will not explain now, but to show that if you prove Arnold conjecture, I will state in a second, on the two torus, which is a symplectic manifold, then you can recover the poincaré-Birkhoff theorem. So that's why it's a generalization of the poincaré-Birkhoff theorem for Hamiltonian systems. So the Arnold conjecture states that if you count the number of one periodic orbits of that the Hamiltonian flow, then you find a lower bound which depends only on the topology of the manifold, the sum of the batch numbers. If the Hamiltonian is non-degenerate, there is a condition for the Hamiltonian to be non-degenerate, which means that all periodic orbits are non-degenerate, meaning that if you look at the linearized flow along any periodic orbit, any such one periodic orbit, then the linearization along the orbits doesn't have the eigenvalue 1, meaning that all orbits are isolated. And all one periodic orbits, if you consider, they exist in a finite number, always have a finite number of periodic orbits. This is the case of the conjecture if the Hamiltonian system is non-degenerate. And there is another lower bound for the number of these one periodic orbits, which is the coupled length of M, again a topological condition of the symplectic manifold in the general case. And this was proved by, this theorem was proved by Ruy Exel, 1983, in the case of the 2n torus. The torus dimension 2n, equipped with the standard symplectic form from R to n. Okay? So this but the direction that I will talk more is the direction, the proof given by Floor in much more general symplectic manifolds. It's for aspherical symplectic manifolds. It's a condition which helps a lot to construct the Floor homology. So let me just remind that I put here the Hamiltonian function to be depending on time. Of course, it could not depend on time. But if it does not depend on time, then you have an autonomous Hamiltonian function. You have a vector field on your manifold, and you look for one periodic orbits. So if you find critical points of the Hamiltonian function, they are particular case of one periodic orbits. So if you can estimate the number of critical points on our symplectic manifold, then in particular we have an estimate of these one periodic orbits. And so as a starting point, we should do some more theory on our symplectic manifold to estimate this very simple case. The Hamiltonian does not depend on time, and you just have to count the number of critical points on our symplectic manifold. So we are in Morse theory. And we let's take a function f, which is Morse on our symplectic manifold. And so this function, let me just, this is the picture that I would like to. We will construct finitely many vector spaces, which I will just so let's take the dimension of our symplectic manifold to be 2n, and we will construct this 2n plus 1 vector spaces. How? When you have a Morse function, you have those local minima, those critical points which have Morse index 0, only finitely many of them. And you can construct this 0 level, which is just the vector space generated by these critical points. So it's a finite dimensional vector space. Then you can do the same with the critical points with Morse index 1, and you can construct another vector space there, generated by those finitely many critical points with index 1, and so on. You consider those local maxima of your function, and you construct this finite dimensional vector space freely generated by the critical points of index equal to n. Okay? This is a construction which depends only on the Morse function. Then the second step for defining a homology associated to our manifold is to define maps. The boundary operator on these two on consecutive vector spaces here is just count. So you take a metric, a Riemannian metric on your manifold, and you consider this vector field there, the anti-gradient, and you look at the trajectories which descend in time, and they start from a critical point and die at another critical point. And then for generic metrics, it's possible to check that you always have, from a critical point with index k to a critical point with index k minus 1, you always have finitely many trajectories, starting here and ending at another critical point there, okay? For generic metrics. So we just count, and that's how we define these maps, okay? So in this picture, let's say the index of x is k, and del k of x is just 2y plus z plus w, okay? Just a linear map, which acts in the generators like that. Okay? We always use, these are vector spaces over Z2, which is much easier to work. Okay? And so we have all these maps from the top to the bottom. This is the boundary operator. And all this set, which depends on a metric, when you to count these trajectories, it's a chain complex. And then you can define, okay, let's say here that inside this vector space you have a subspace here, which I will draw in this color, which is the kernel of this linear map. Okay? And also inside this space here, that is the image of the map in the level above. Okay, but it's the good part of this theory is that if you iterate twice this map, it's always 0. So the boundary of the boundary is also 0. Okay? So and in this way, when I said that there is two subspaces inside here, one coming from the image in the level below, and the other, which is the kernel of this map, using the fact that if you take the square of this map is always 0, then the image of del k plus 1, let's put here another level, c k plus 1, the image of this map is inside the kernel of this other map. So there are two subspaces inside there, and these two subspaces strongly depend on the data, which is the Morse function and the Riemannian metric that you use it to compute the trajectories. But when you take the quotient of the kernel to the image of del k plus 1, it doesn't depend on the data anymore. And this is called the homology of our chain complex. And for instance, if the homology is non-trivial, when you take this and you have certain dimension of this homology, this gives you a lower bound on the number of critical points. So whenever you put a Morse function there, you need to have enough elements to produce that homology. So it gives you a lower bound on the number of critical points. So that's how Morse homology works. And why it works? Well, there's a picture that explains a little bit this construction. Why del square is equal to 0? Because so if you take a trajectory connecting this critical point of index k plus 1 to another critical point to index k minus 1, so this trajectory here always lies, again generically for a generic Riemannian metric, always lies in a one-parameter family of trajectories. And the worst case, when this one-parameter family breaks, it will always break this way here, in a trajectory from x to index k critical point, and a trajectory from y to z. That's the worst case that can happen for a trajectory. This is space of trajectories connecting x to z. It might break on this broken trajectory with a critical point in between. So when you compute d square in this picture here, you see that this diagram here always produces 0, because we are in z2 coefficients. So del square of x is 2z, and 2 is equal to 0 in these coefficients. So that's how things work fine. Okay, so let's go to Floor homology. Floor homology is an attempt to do exactly the same thing that was done for Morse homology. But instead of considering a finite dimensional manifold and a Morse function on this, and work with the gradient trajectories of associated to a metric in that manifold, we do almost the same thing in an infinite dimensional setup. So we consider the space of loops inside the manifold, smooth loops, and there is a function inside the space, which is just you integrate the symplectic form over a capping disk for the loop. So we always consider contractible loops, so these capping disks always exist, and integrate also the Hamiltonian function against this loop. So we have a function, a real function here, in this space. Of course, we need some extra hypothesis for that to work, but I will say that in a minute. And so we have this function. The critical points of this function are exactly those one periodic orbits that we have. Okay? So this is the variation of principle of this problem. And instead of considering those gradient trajectories connecting critical points, here is almost the same thing. We consider holomorphic curves. These are solutions to certain PDE, which I would just call holomorphic curves. This equation here, defined on a cylinder, and with coordinates S and T. And solutions to this equation connects critical points of the action function in the same way that we have in the Morse setup. And so we study this set of solutions with bounded energy. There is some notion of energy. So that this is always the case that I said, exactly this picture here. So we have these one periodic orbits, and if we have a solution, a holomorphic curve, which is just a cylinder with finite energy, then the cylinder, in one end of the cylinder will converge to a periodic orbit with period equal to 1, and in the other end to another periodic orbit. And you can construct this same object here. But now with the grading, instead of taking the Morse index in each level, we take what is called the Conley-Zehnder index, which is natural for Hamiltonian dynamics. Okay? In this picture here, we have this boundary operator between the level k minus 1 and del k of this periodic orbit is just the sum of these three periodic orbits. So we replace the critical points of a Morse function with this one periodic orbit, and we count these trajectories. And under some good conditions, but now it's much more technical, much more difficult to prove that del square is equal to 0. This is the main difficulty of building this theory. But it turns out that if you assume some good properties of your symplectic manifold, this is true. Okay? So that's the hypothesis that one of the hypotheses of the symplectic manifold being aspherical, which means a lot. Means, for instance, that this action functional is well defined as a real valued function. It's like, for instance, if you take different disks, different capping disks for your periodic orbit might give different number, but this condition implies that it doesn't matter which disk. And also another condition which says that the grading is well defined, meaning that the Conley-Zehnder index of each periodic orbit, which plays the role of the Morse index, is a well-defined integer number. And so under such conditions, it's still true that del square is equal to 0, and you have a chain complex. You have the homology of this chain complex generated by the periodic orbits. And it turns out that in the end, all these homologies coincide with the singular homology of the manifold. Okay? Also the Morse homology and the Floer homology, they all coincide with the singular homology. And finally, I will just put a picture here. So Umberto is giving the second half of this talk, which is just to give an idea of the difficulties that show up here that we have to deal with. It's like the daily job of somebody who works in this area, is trying to understand the compactness of these cylinders. For instance, the cylinders which is if you take, for instance, a periodic orbit with Collinsender index k plus 1 and a trajectory, this holomorphic curve connecting with the periodic orbit with Collinsender index k minus 1. So the difference is equal to 2. So generically, this solution lies in a one-parameter family of solutions. And we would like that the same holds in the Morse, as in the Morse case. For instance, the worst case, if you consider of this family, in the end, if it's not compact, if it breaks, it will break exactly as a pair of cylinder connecting one critical point with Collinsender index in between. That point P is in there. But of course, now the PDE is much more difficult. Have a two-dimensional domain. The situation is much harder. Instead of happening this type of picture, which would be good to prove that del square is equal to 0, you might have the formation of bubbles. And in this case, Floor homology a priori would not be defined in this way. So we, with those hypotheses that I said, for aspherical manifolds, technical hypothesis, it never happens, this type of bubble. So you always have this picture, the homology is well defined, and it turns out that it coincides with the Morse homology, meaning that you can work with this type of construction to show that the floor homology that you will obtain for a Hamiltonian function is the same as if you work for another Hamiltonian function by deforming the data, and you show that doesn't depend on this deformation. And if you consider the Hamiltonian function to be C2 small, then the chain complex of floor, which is generated by periodic orbits, it's possible to prove that if H does not depend on time and is C2 small, then it really coincides with the Morse chain complex. So the homology is exactly the same as the Morse homology, and in particular, it coincides again with the singular homology. So I haven't said anything about an extra data, because to construct Morse homology, we used a metric, a Riemannian metric on the manifold. But to construct the floor homology, this floor chain complex, you used also an extra data, which is an almost complex structure on the symplectic manifold. So Gromov observed that symplectic manifolds are kind of complex. They admit an almost complex structure. And so we can talk about these holomorphic curves. In fact, when you see this equation, the floor equation, here you see this J, which is just this almost complex structure, which plays the role of the Riemannian metric. And this J, of course, has nice properties, and if you choose J generically, all this construction will behave nicely. So this is an idea of the philosophy of working with homology. I just said about Morse homology, a little bit of floor homology, and our paper deals with the contact homology, which is a special case or a situation which deals with these Reeb flows instead with Hamiltonian flows. But I will stop here, and Humberto will continue from now on. Okay.
Alô? Alô?
before I actually go on, I also take a few seconds to, no? I don't think it is. Alô?
Deixa eu aumentar, aumenta.
Oi. First of all, I want to start by saying that I'm so honored to be this talk right now. And okay, so and I'm very happy to have shared this prize with Pedro, and I'll keep on explaining things about the Morse theory of the action functional. So as Pedro said, we use this other version of Morse theory for the action functional, which is called contact homology. So first of all, I'd like to explain what is contact homology. But instead of explaining exactly what it is, I'll try to answer this question by not answering it. I'll try to answer this other question here, which is I'm going to try to explain what's the difference between Floor homology and contact homology. Okay? So as Pedro said before, Floor homology is a Morse homology for the action functional. And but as he explained, genetically you have to take non-autonomous Hamiltonian functions so that you actually get the action function to be a Morse function in some infinite dimensional setting. But also we would like to so what he explains is a good tool to finding orbits which are periodic but with fixed period, right? So Floor homology here, that's what's written here. Floor homology is a good tool for finding orbits, periodic orbits with fixed period. And contact homology is a good tool for finding orbits of Hamiltonian systems which are autonomous and which have fixed energy. So by going from Floor homology to contact homology, you're changing the problem. Instead of studying the action function for finding periodic orbits with fixed period, you're trying to find periodic orbits with fixed energy. So you try to work on a fixed energy level. Okay? So according to Eva Eklund, this is harder. And because it's harder, it requires more sophisticated tools, and that's contact homology. I don't think you can see what's written here, but for example, if you want to try to prove a multiplicity of results for periodic orbits, it's harder to work in this setting because when the energy is fixed, you cannot fix the period. And so a single orbit can be iterated and generates infinitely many critical points. Right, so you have a problem. You don't want to find the same orbit iterated, right? If you want to prove that there's two, you don't want to find one and the other one, which is the first one iterated. So, okay. All right. So, having said that, I need to say that the seed of the analysis necessary for this new kind of Morse type theory for the action function was introduced by Helmut Hofer in his groundbreaking work for the three-dimensional Weisstein conjecture. Unfortunately, it doesn't work for the general energy level. You have to work with special kinds of energy levels, and it works, for instance, for contact type energy levels, which is something I'll try to quickly explain. So he introduced, this is a picture of Helmut Hofer. He introduced these holomorphic curves, these special holomorphic curves in symplectizations in this paper from 1993. And then the properties of these holomorphic curves was further studied by a long series of papers by Hofer, Vysotsky, and Zander. This is Chris Vysotsky, and this is Edward Zander. And then later, this theory was expanded by many authors. So let me just say what's a contact type energy level. It's an energy level for which there is a Liouville vector field. It's just a Liouville vector field, which is a vector field which satisfies this equation here. You contract. If you do the Lie derivative of the symplectic form with respect to this vector field, you still get the vector field with the symplectic form, which means that the flow of this vector field generates an infinite. So this vector field is to be thought of as an infinitesimal symplectic dilation. The flow expands the symplectic form like that, right? So if the energy level, which I'm calling here the hypersurface, is transverse to this vector field, that's the contact condition. Let me just say what's a contact form. A contact form is, this is a mysterious definition here, is a one form which satisfies this equation. So the energy level here has codimension 1 inside the phase space. And then that's the picture. I mean, if you take the Liouville vector field, is transverse, which is assumed to be transverse to this energy level, if you contract it with the symplectic form, restrict to the energy level, you get this one form, which is a contact form. Every contact form arises this way. So energy levels that have this structure are good for holomorphic curves. Example, you take standard symplectic structure in R2n. You take this radial vector field here. So every star-shaped hypersurface is going to be transverse to this guy, and it's going to be a good energy level to be studied with these techniques. Okay. So this is a good set of examples to keep in mind of good energy levels. Here's another class of good energy levels, which are unit sphere bundles inside cotangent bundles. Right? So you have a metric, you want to study the geodesic flow, that's a good kind of energy level too. Okay. So this contact form, which is this slightly crazy one form, induces a lot of structure on the energy level. It induces a contact structure, which is the kernel, and induces the Reeb vector field, which is uniquely defined by these two sets of equations. This is the most important equation here. This is saying that this vector goes in the kernel of the symplectic structure restricted to the energy level. It's the vorticity direction. This is just a normalization condition. Right? So you see, this vector field is going to be tangent to the energy level, and it's just going to be a reparametrization of the Hamiltonian dynamics. This is another way of reparametrizing the Hamiltonian dynamics. So studying Reeb dynamics on a contact type energy level is the same thing as studying the Hamiltonian dynamics of that level. Okay. Another thing that is associated to this contact form is the symplectization, which is the manifold R cross M with symplectic form, looking like that. This symplectic manifold doesn't depend on lambda, although it's a little strange because you see lambda here. Take another lambda, you're going to have a symplectomorphic symplectic manifold. All right, so then you're going to be studying holomorphic curves sitting inside the symplectization of the energy level. So for that, we choose some complex structure on the contact planes, which is the kernel of the contact form, and extend the symplectization by declaring that J is taking the radial direction to the Reeb direction. Right? Okay, so we have an almost complex structure on this even dimensional space. And Hofer introduced this definition, a map from a punctured Riemann surface. So S is a Riemann surface, gamma is a finite set of punctures. So this map is defined on the complement of this set of points. It takes value on the symplectization, and he calls such a map a finite energy surface if it's holomorphic, and it has non-trivial finite so-called Hofer energy. Some crazy definition here, but it's some sort of definition which is suitable for working with symplectization where you have these translations on the vertical direction. Okay, so this is just the analytical object which is going to substitute solutions to Flower's equation that Pedro described, which is going to be used to defining this different kind of Morse theory for the action function. Cool. So here's a main theorem by Hofer. It says that Reeb dynamics has a periodic orbit if and only if there exists a finite energy surface on the symplectization. Here's a picture of the theorem. So when you have such a map, so the domain of this map is this Riemann surface with a bunch of punctures, and then in the symplectization, the image looks like that. As you approach the punctures, the image of the map is sort of approaching a trivial cylinder over a periodic orbit. That's the finite energy condition playing a role there. So you find periodic orbits as limits of the curve at these punctures. Okay, so here's the symplectization direction, this is the R direction, so things go up plus infinity like that, or minus infinity like that, approaching periodic orbits. So for doing contact homology, the picture is sort of the same as in Floer homology, but so again, you're going to be considering these complexes generated by periodic orbits, the gradient also coming from the Cohn-Lysander index, and the differential is defined by counting cylinders connecting these orbits. They look like that. So here you have these orbits there. You look at the trivial cylinders, which is just R across the orbit. You have these cylinders there. Right? These are actually holomorphic curves. And then the holomorphic cylinder is looking like that. So the domain is a punctured sphere, and it's asymptotic to x, and let's say this one is going from x to y. The holomorphic curve equation should be a replacement for the anti-gradient flow of the equation for the action function, and then you have a homology looking like that. So here's how we usually draw this kind of picture. And this is a typical cylinder contributing to a term, to the y coordinate of the dx term, right? So x is a generator in degree, let's say, k, and y is a generator in degree k minus 1. And counting this solution, the solutions of this PDE is contributing to the count that you see here. So you see in this picture, one difficulty in this picture is that you have lack of compactness of the target of our holomorphic curves. And all Moming's thesis introduced a version of this theory. Oh, I cannot read what's, you cannot read what's behind here, but he introduced a version of this theory in the complement of a bunch of Reeb orbits. So you have a bunch of Reeb orbits, and you remove these Reeb orbits, and you have a contact manifold, which is non-compact already. And then, again, you can have the symplectization direction is another source of non-compactness. So I have two sources of non-compactness, and then Moming managed to define some version in very special situations of this kind of homology. Okay, I'll come back to that. So what's that? What does all of that have to do with the poincaré-Birkhoff theorem? So we focus on this kind of dynamics here. Talking about, from now on, I'll be restricting to contact type energy levels, which come from star-shaped hypersurfaces in R2n, actually in R4. Instead of looking, you can look from this point of view, or you can look from this point of view here, which is for each star-shaped hypersurface, you can associate a function on S3, and then instead of looking at the actual hypersurface, you look at S3 with this kind of contact form, which is some positive function times the restriction of the standard Liouville form, standard primitive of the symplectic form, right? So instead of looking at all possible hypersurfaces, you can look at all possible such functions. What happens when the energy level is strictly convex? That was a major theorem by Hofer, Vysotsky, and Zander. In the case of strictly convex hypersurface, you have a very special periodic orbit, which has nice properties, and which bounds an embedded disk, which is a global surface of section for the flow. Let me just draw a picture here. So I'm talking about what happens to the dynamics when the energy level is convex. So in that case, you see this special periodic orbit. It bounds a special disk, which is transversal to the Hamiltonian dynamics. And Actually, this is only a page of a whole open book of this energy level. It's a foliation. I mean, if you remove this orbit, you have a foliation by planes, by disks, and the return map to this disk is well defined. So there is a global surface of section for the dynamics. In particular, if you look at a fixed point which you would get from applying Brouwer's translation theorem, you would have this Hopf-Link, this pair of periodic orbits, right? If you apply results by John Franks, you prove, for example, in this case, have 2 or infinitely many periodic orbits. So that's a very strong description of the global dynamics in this very general class of energy levels. So from now on, I want to just keep that in mind. Keep the Hopf-Link. This is exactly the situation encountered by Poincaré. Poincaré studied, what Pedro described in the beginning of the lecture. Poincaré studied the restricted three-body problem. He found such objects. And he managed to find annuli, which have boundary on this pair of orbits, which are also global surfaces of section. That motivated him to state the poincaré-Birkhoff theorem. Right? So the twist condition that would get to if such a global surface of section would exist, and if we wanted to apply the poincaré-Birkhoff theorem, the twist condition would be coming from linearized dynamics at these orbits. This is, so here you see an orbit going like that, and associated to this orbit we have a real number, which is the transverse rotation number. So how do you define a transverse rotation number? So you take so you see, the linearized return map maps fix a point, and the linearized return map map associated to this period is going to map the contact plane to itself. It's just a symplectic map on this 2-dimensional plane here, right? So you can take a vector, then you apply the map, you have another vector in the plane. So you think about the set of directions of the rays. Think of it as an S1 worth of directions. Then you have a rotation number, which of course depends on the trivialization of the contact structure that you choose along the orbit. If you change the trivialization, the rotation number is going to change. The rotation number is defined modulo Z, but if you fix the trivialization, the rotation number is defined as a real number. Okay? So that's the main statement of our theorem in collaboration with Nome. So it's a collaboration between myself, Nome, and Salomão, which says something about star-shaped energy levels in R4. Suppose you have a Hopf-Link, and let R0 and R1 be the associated rotation numbers. Right? So I'm going to introduce a notation here quickly. So I think my time is up right now. I think I'll take 2 or 3 more minutes. So I'll say, so for example, you have U, V, W, 3 vectors in the non-zero vectors in the plane. Let's say remove the 4th quadrant. For example, when you see something like that, I'm going to say that, so if the vector is more advanced in the counterclockwise direction, I'll say a vector is bigger than the others. Right? So in this picture, V is bigger than U, or W bigger than U, right? W bigger than V, right? So just a notation. So if you make these vectors here, R01 and 1R1. So R0 and R1 are the rotation numbers associated to the components of the Hopf-Link. If you take a relatively prime pair of integers between these guys, doesn't matter which one's where, then there is a periodic orbit in the complement of the Hopf-Link, which links, let's say this vector is coming from the integer lattice, has coordinates P and Q. This orbit is going to link P times with one component of the link and Q times with the other component of the link. You see, if there was, let me explain the theorem here. If there was a disk-like global surface of section whose boundary is P0, if you remove this fixed point, would have an open annulus, and that conditions on the number p and q would be exactly the conditions for the fraction p over q to lie in the twist interval for which the Poincaré-Birkhoff theorem applies. So it's exactly a generalization of the Poincaré-Birkhoff theorem for flows. Here's another picture of this statement. You have these two vectors made out of the rotation numbers. So for each point in the integer lattice lying between this open sector here, you have a periodic orbit. P is the number of times it links with one and Q with the other. But this time there is no map, there is no global surface section. That's the whole point of it. And this, so for example, here's a picture for this such an orbit where P is equal to 7, links 7 times with this component and links 1 times with this component. And where are these orbits coming from? They are coming from the Morse homology of the action function, right? So I guess I'll stop here. Thank you very much.
Questions?